Statistical inference means that we use the information collected from a sample to draw conclusions about the population. So far, we discussed two types of inferences, and both of these procedures use the mean of a sample. The purpose of the first procedure is to estimate the population mean based on the sample mean by computing a confidence interval. The second procedure is a test of statistical significance for the difference between the sample mean and the given value, which is often the population mean. In both cases, the estimation relies on the properties of the normal curve, and therefore we use z-scores in the computation process. That's why these procedures are also called z-procedures. Needless to say, when the variable we're working with does not have a normal distribution, these computation procedures should not be used. To be able to use the z-procedures, certain assumptions must be met. I already mentioned the first assumption, and that is that the data should have a normal distribution. However, real data are rarely going to be perfectly normal. A distribution that only resembles the normal curve and is not strongly skewed is often considered acceptable. Even more important than a normal distribution is the sampling procedure. And this leads us to the second assumption, and that is that individuals in the sample were randomly selected for the study, so every individual in the population had an equal chance of participation. We know very well, though, that selecting a random sample is difficult and is expensive, especially if the sample is large. Therefore, many studies do not use a random sample. Now, in these situations, researchers must rely both on their knowledge in the field and their methodological expertise to decide whether the sampling selection procedure is acceptable and whether or not it would induce any bias in the results. Other issues such as non-response, low response rates, using inappropriate data collection procedures, and flaws in the design of the study have a strong impact on the quality of the results and are even more important than the shape of the distribution. Let's discuss first the issues that we must consider when computing confidence intervals. We learned that when estimating a population mean, in order to obtain a confidence interval, we must first compute the margin of error. We know that if we select several random samples, for each one of these samples, the mean is going to be slightly different just because individuals were randomly selected. This is called sampling error, and the margin of error represents the amount of error that may be induced in the estimation process due to random sampling. However, the margin of error does not take into account other potential sources of error, such as undercoverage or non-response. That's why we have to specify such limitations when reporting our results, and when we read the results published by other researchers, we must always take into account these issues when interpreting the results and their significance in the field. We know enough now about these assumptions to be a little bit more critical and not put so much weight on everything that is published. When we estimate confidence intervals, we know that the larger the sample, the smaller the margin of error. However, selecting a large random sample is not only very difficult but also very expensive. So when we plan a study, we need to decide how many individuals we should include in the sample to have a reasonable degree of estimation confidence and at the same time to have a relatively small margin of error. To identify the ideal sample size for our study, we can use the formula for the margin of error. So in this case, we go backwards, if you will. We first have to specify the confidence level that we want to have, like 95% for instance, and the margin of error that would be acceptable. For instance, for IQ testing, let's say that a margin of error of 3 points would be acceptable. And if we want to have a 95% confidence level, then the value of z star will be 1.96. We also need to know the population standard deviation for our variable, and we already know that for certain IQ tests, this standard deviation is 15. So if we have all this information, we can then find the sample size, or the n, based on the formula for the margin of error. We can compute n by first multiplying z star by the standard deviation, and then dividing this product by the desired margin of error. The number obtained from this division is then squared, and the result represents the size of our sample. So for our example here, the result is 96.04. Because we're talking about individuals, decimals do not make much sense, so we should round this value to the nearest integer. Based on this result, we can then say that if we want to estimate the population mean with a 95% confidence and with a margin of error of 3 points, then the sample should include at least 96 individuals. Let's talk now about some practical issues related to the test of statistical significance. When we have to decide whether or not the null hypothesis should be rejected or accepted, the most important criterion is how small is the p-value. We already know that we must compare the p-value to the significance level, to alpha, and if the p-value is smaller, then we can reject the null hypothesis. However, a good researcher must take into account some other factors as well, and to have some flexibility. For instance, if the p-value is only very slightly lower than alpha, like 0.049, should we still reject the null hypothesis? Well, the decision depends on the nature of the research project, how much room there is for error, or how strong is the null hypothesis in our field, and what are the consequences of rejecting the null hypothesis. If the null hypothesis is a fundamental principle in the field, then we need very strong evidence to prove that such a principle is in fact not true. A very small p-value would be preferable to a value that is only slightly below the cutoff. Similarly, if rejecting the null hypothesis has very important consequences, like having to redesign an instructional program or having to redesign a standardized assessment, then we should have very strong evidence or a very small p-value to reject the null hypothesis. Another issue that I would like to mention is the importance of choosing the most appropriate alternative hypothesis. As you know, a two-sided alternative hypothesis states that the sample mean can be either lower or higher than the given value. So you may wonder, why bother having a one-sided alternative hypothesis when we can cover both possibilities with a two-sided alternative hypothesis? Well, the problem is that when the null hypothesis is two-sided, we must multiply the value to the right of z by 2 to obtain the p-value. So the p-value is going to be larger. Because the p-value is larger, it is less likely that this p-value is smaller than alpha. So it is more difficult to reject the null hypothesis, which is our purpose. This is why it is preferable to choose a one-sided alternative hypothesis when we have enough information to justify this decision. If we look again at the formula that is used to compute a test statistic, we can see that the standard deviation of the population and the sample size are both taken into account. Both of these have an impact on the test statistic, and therefore may influence the results of the test. Let's talk about the standard deviation first. If a variable has a large standard deviation in the population, meaning that its values vary widely across individuals, then even if the recorded difference is large, there is a good chance that this difference is not statistically significant. For instance, let's say that we're measuring adult learners' attitudes toward online learning. These attitudes may vary widely across individuals depending on age, profession, level of education, computer skills, and so on. If we select a sample of students from an online graduate program, then their opinions may be very different than the mean for all of the adult learners. But this difference may not be statistically significant given the variability of these attitudes in the general population. Similarly, the size of our sample also has a strong weight on the results. When the sample size is large, even a small difference is likely to be statistically significant. Results have a different weight for a sample of 15 learners, 1,500 learners, or 15,000 learners. The larger the sample size, the more weight the results have, and the more likely it is for the recorded difference to be statistically significant, even if this difference is a small one. When conducting a test of significance, we have to use the evidence collected from the sample to make a decision about the null hypothesis. Of course, we do everything in our power to make sure that our decision is the correct one. However, the laws of probability tell us that there is always a chance that our decision may be incorrect. If we think about the decision that we have to make, we realize that there are 4 possible scenarios. As shown by the columns in this table, the null hypothesis can be either true or false. On the other hand, the decision that we make about the null hypothesis can be to either accept or reject the null hypothesis. If we accept a null hypothesis that is in fact true, we obviously made the correct decision. Similarly, if we reject a null hypothesis that is in fact false, we also made the right decision. The ability of a statistical test to reject the null hypothesis when it is false is also called the statistical power of a test, and is represented in the upper right cell of the table. The power of a test can be computed, usually by using statistical software, but these computations can be quite complex and are beyond the scope of this presentation. There is also a possibility of making a wrong decision, and there are 2 types of error that we can make. When the null hypothesis is true, but we reject it, then we make what is called a type 1 error, and we already know that alpha is equal to the probability of type 1 error. If the null hypothesis is false, and we accept it, then we make a type 2 error, which is also called beta. What is important to understand here is that there is a trade-off between the 2 types of error. If we want to reduce the probability of making a type 1 error by reducing the alpha or the significance level, we automatically increase the probability of making a type 2 error. Depending on the type of research that we are conducting, we must decide which one is less detrimental to our study. In general, consequences are not as severe if we reject a hypothesis that is true than if we accept a hypothesis that is false. For instance, in medical science, when a drug is tested, the consequences may be less severe if the researchers decide that a new drug does not produce significant improvement when in fact it does, than if they decide that they should use drug and that the drug is effective when in fact it isn't. Of course, in social sciences, the consequences are not as dramatic. I just chose this example to better illustrate the relationship between the 2 types of error.